So today we are going to talk about how we can use contextual bandits to develop interactive recommender systems and perform more efficient A/B testing. So let me start by explaining what traditional A/B testing does and what can be the issues with it. So let's say that we have a new feature which we want to roll out, but we can't just launch it because we are not sure how good it will perform. So what we do is we direct X percentage of the traffic of our website to this new feature, and the rest of the traffic still goes to the old or the current service. So to perform this experiment, we direct the traffic like this, and then we keep on collecting samples until we are statistically sure that the new feature is better than the old one. So the problem here is that while the experiment is going on, we see that if the new feature is way better than the old one, or if it's way worse than the old one, we cannot adjust X dynamically. We have to wait for the experiment to end. And contextual bandits can especially help here because they provide a very good online learning framework where they can react to feedback very quickly. What that means is that if they are seeing that the new feature is performing way better, they will increase the X so that less traffic goes there, and this reduces the cost. And just think if you have a lot of variations. I'm just showcasing 2 here, but if you have 10s or 20 variations, then it gets even harder with A/B testing, and their contextual bandits can be very helpful. So that was the first application. The second application we are going to discuss is recommender systems. So as you all know, recommender systems are everywhere. All major web-based companies make heavy use of recommender systems. And the reason is simple, that we live in an era of information overload. There's just so much content. So we have to decide which content to show to which users and at what time. So they are extremely important. Now, a typical, so traditionally, recommender systems are trained in an offline manner. So what that means is, so this is a typical offline recommender timeline. So users interact with the items on the website. The feedback that they might give can be implicit, which means things like clicks, dwell time. So implicit feedback is something from which we can't say for sure that the user liked that item or not. And then the feedback can be explicit, like ratings, and likes, and dislikes, and so on. So we collect this data set, and then we train a model. And over the course of time, new users arrive, new items arrive. New users interact with new items and old items, and more interactions happen. And then finally, we retrain the model. And this cycle goes on and on. There are certain issues in offline recommender systems. So the first one is frequent retraining. So first, it's very hard to decide how frequently to train, and then on what data to train. Typically, what we do is we just retrain on all of the historic interactions data again and again. And as the volume of this data is increasing at a very fast rate, retraining becomes computationally more and more expensive. The second problem is that new users and items keep on arriving, and we usually don't know much about the new users and items until we do exploration. So what that means is a new user comes, we need to show a diverse list of items to the new user to understand his or her preferences. Similarly for items, if we don't showcase the new items to the existing users, then the new items won't even get any interactions from the users because they might get lost in a lot of other old popular items. So this highlights the need for exploration. So we need to look into diversity. We need to recommend items about which we don't have a lot of data. But how to do that? That's the question, and that's what contextual bandits can answer. There's another benefit of exploration in case of recommender systems. And if you think about it, recommender systems is a partial feedback problem. So what I mean by that is, let's just contrast recommender systems with supervised learning. So in supervised learning, let's say we have 10 labels or 10 actions. And let's say that the model recommends action 1 or label 1. So since we have label data, we can actually tell the model, hey, label 1 is not the right one, label 5 is the right one. So you need to adjust your loss function and retrain the weights. In case of recommender systems, if we recommend item 1, we will get a reward or feedback only for the item 1. And the system won't know anything about item 5. item 5 can be the best one in this case. So the only way the system can discover this is by recommending item 5. So hence, there's this need of exploration. Finally, this is perhaps the hardest one, which is changing user preferences, or if the popularity of certain items just jump. So let's take a case where it's the Oscar season, and so if it's the Oscar season, like a lot of movies that got nominated for Oscars might gain certain popularity. And the problem is, if we are not retraining our model frequently enough, we won't be able to capture this fact. Okay, so we'll have to bring in some heuristics. We'll have to have manual intervention to take care of these suddenly popular items. And same holds for user preferences. User preferences might change gradually over time. If we don't figure this out in an automated way, then again, it's a big issue. So Contextual Bandits, again, because of the online learning framework and exploration-exploitation trade-off that they can manage really well, they can handle most of these practical issues. So the agenda for this talk is going to look like this. So I have already given you some motivation as to why Contextual Bandits are useful in these two applications. Now I'm going to talk about in details how bandits work, how the different exploitation policies function. And then I'll be presenting some extensions of bandits. So one extension is contextual bandits, where we take contextual information into account. And then I'll also show you how we can extend bandits to ranking. Finally, we'll present a use case where we'll showcase how we can use all these learnings, contextual bandits specifically for ranking, and implement them to develop a interactive movie recommender system. And finally, we'll just talk a bit about the reinforcement learning offerings on SageMaker. Okay, so let me start by bandits. So bandits provide a very good mathematical framework, which looks like this. So we have an agent, which is the brains, which is the main algorithm, and then we have an environment. So the agent keeps interacting with this environment by taking certain actions from an action set, which might be fixed or dynamic. At every time step, it takes an action, and it gets a reward for the corresponding action. And this cycle goes on and on. So the agent is basically collecting these rewards over time, and its job is to maximize the cumulative rewards. Other way of putting this is it wants to minimize cumulative cost or regret. I'll talk more about regret in a couple of slides. At every time step, the bandit has to decide between these two. So it has to decide whether it should explore, it should try other alternatives, discover new things, or whether it should exploit. What that means is whether it should take the action that it thinks it's the best one. So it has to exploit for performance. This X percentage keeps on varying dynamically. There are different algorithms which can adjust this X over time. So we'll see how that works. So just some terminology, because I'll be using these terms throughout the presentation, so make sure you understand them perfectly. So the most important term here is Q value of an action. So the Q value of action is nothing but the mean reward for that action. So from the equation, it says QA is basically the expectation of rewards given an action. So we have an expectation term there because the rewards can be stochastic. I might get a reward of 1 for the same item, but some other user might get a reward of 0 and so on. So expectation is nothing but, if we take this arm like thousands or millions of times, then what's the mean reward that we would get? The bandit doesn't know this true Q value. It has to estimate that over time. How it can do it, a simplest estimate can be just maintain a mean of rewards that the bandit sees so far for all the actions. So let's say that the bandit executed action 1 5 times. It got 5 rewards. So Q estimate for action 1 is basically just the mean of those 5 rewards till time step t equal to 5. And finally, the objective function that bandit is trying to optimize for is to minimize this total regret, which is defined by the Q star. So Q star is basically the reward, the expected reward that the optimal arm gives. So there's an assumption here that there's one optimal arm which gives like the highest reward. And then QA tau is basically the reward of the arm that the bandit took at time tau. And total regret is just expectation of summation of this term. Okay, so let's see how bandits compare to A/B testing through this layout optimization problem. So the problem looks like this. So we have 3 different layouts, and we want to test which layout is the best for our users. We are going to do a simulation run. So we have to fix like which layout is better in terms of these true Q values. So for this layout 1, like the true Q value is 0.3. What that means is that 30% of the times users will like this layout, and 70% of times they will dislike this. So it will produce a reward of, so if we take action 1, then it will produce a reward of 1 with 0.3 probability. And similarly, we have QA2 equal to 0.5, like 50% success rate, and then A3 is 65, which is like 65% success rate. So let's see how bandits solve this problem. Just before I go into that, I'll explain different exploration policies that bandit can use, and then I'll just apply one of this exploration policy to the problem that I just set up. The simplest that's fine. It doesn't have to add up. So these are different independent layouts. So layout 3 can be liked by users 65% of the times. Yeah, these are like independent distributions. Okay. So the simplest exploration policy that we can use is epsilon greedy. Here what we do is we fix a number epsilon. Let's say we fix it to 0.2. What that means is that the bandit will explore an action at random with 20% probability, and it will exploit. What that means is it will take the best action 80% of the times. And how it decides what action is the best, it does that by looking at the Q estimate that it's maintaining. Okay? In practice, like this is the simplest exploration algorithm, and it's very easy to understand what the bandit is doing. But the problem here is it's hard to adjust this epsilon over time. So think of a case where, let's say we fix this epsilon to 20%, and we have executed a lot of time steps. The bandit is now confident as to which action is the best. But if we still keep on exploring 20% of the times, we might be hurting the performance a lot, and this will start incurring a lot of costs. So that's why we have these other approaches, which basically fix this, decide this epsilon dynamically. These approaches are based on uncertainty. What that means is that whenever the bandit is trying to calculate these Q value estimates, it also computes some uncertainty estimates for the Q value of every action. And then it tries to use that to decide when to explore or when not to explore. In simpler terms, if it's not confident about a particular action, then it'll try to execute that action more number of times so that it at least becomes reasonably confident about that action. So let's first look at UCB. It's called upper confidence bound, and it's based on the idea of optimism in the face of uncertainty. What that means is, at every time step, the bandit will maintain the Q estimate, which is the mean of these distributions, but it will also maintain some uncertainty around this mean. It does that using that formula, but I'll try to explain that using this graph. So on the x-axis, I have the estimated Q values, and these curves are the probability distributions of these Q values. So wider the curve, the more uncertain the bandit is about a particular Q value. In this case, it's most uncertain about the blue action, which is action 1, and it's the most certain about action 3, which is the green one, because it's not so wide. Now, how the bandit decides which action to take. So if you look at the extreme, the right extreme of this plot, like the blue action, even if the bandit is very uncertain, like it gives the maximum Q value. So in this case, bandit will execute the blue action. Once it executes the blue action, if you look at the formula above, so I have this NTA in the denominator. That says that this is the number of times a particular action has been executed. So as that number increases, the whole term decreases, the uncertainty estimate decreases. What that means is this blue curve will shrink. And in the next step, then maybe the red curve is the most optimistic one, given the uncertainty, and then the bandit will execute the red action and so on. So this is how the actions will be taken, and over time you can imagine that all these curves will shrink, and finally we'll have a winner. Yeah. So that's the optimal action. There's another algorithm which is based on uncertainty. It's called Thompson sampling. It's very similar to UCB. One thing to note here, sorry, in case of UCB, is that the bandit is not explicitly maintaining any probability distributions. This is just for the purpose of illustration. all the uncertainty estimates can be taken care of by that formula. Whereas in Thompson sampling, what we do is, we maintain specific probability distributions across the Q values of each action. So this will just become more clear in a moment, but what we do is, let's say that at a particular time t, we have these 3 probability distribution functions for the 3 actions that we have. Now what we do is, the bandit needs to choose an action, so it will sample a value from each of these distributions. So what does sampling mean? So we have a blue curve. So we'll sample like a number around 0.3 with the highest probability, because we have the peak there, but we might also sample numbers up to 0.8. So let's say in this case, bandit samples 0.7. Similarly, for the orange one, it might sample 0.4. For the green one, it might sample 0.6. So even though the mean of the blue curve is the least, but because it's so uncertain, the bandit sampled a reward which is maximum for the blue curve. So in this case, bandit will execute the blue action. And again, similar to as I explained for UCB, this blue curve will shrink over time. We can update this blue curve using the reward that we'll get for the blue action. And I'll show you how we can update this curve. So getting a bit more concrete, how to perform Thompson sampling, let's pick this particular bandit, which is called the beta Bernoulli bandit. Now, let me explain what these distributions mean. So Bernoulli, we call it Bernoulli because each of the action or each of the arm is a Bernoulli distribution. So Bernoulli distribution is like a biased coin toss with parameter theta. So again, if we take action 1, then 30% of the times you'll get success, rest of the times you'll get a failure or reward of 0. So that's the Bernoulli part. So we start a simulation run. So all these true Q values, like 0.3, 0.5, and 0.65, they're unknown to the bandit. We are doing a simulation run, so we have to fix that. But it's unknown to the bandit, and the bandit needs to estimate these Q values over time by interacting with the environment. How the bandit can estimate them? It can assume a beta distribution for each of these true thetas or each of these Q values. What is beta distribution? It will become clearer from a graph, but just remember that beta distribution has 2 parameters, alpha and beta, and these define, what's the mean of the beta distribution, what's the spread look like, and so on. And the parameter update rule is again very simple for this distribution. So basically, if we choose an action, we get a reward of 1. We'll just increment the alpha for that action by 1. Otherwise, we'll increment the beta for that action by 1. So that's the update rule. That's how we keep on updating these distributions over time. Now let's see what this looks like in practice. So this is the starting condition. Here, what we have done is we have set alpha equal to 1 and beta equal to 1 for all the 3 arms. So these distributions are flat. They are very much similar to uniform distribution. Bandit doesn't know anything about the rewards or the Q values. We start the simulation, and then the curves look like this. So at each time step, what is happening is the bandit is taking action by sampling rewards from these curves. It takes the action which gives the maximum sample, and then we update the posterior, we update the parameters using this update rule. And as we update alpha and beta, these curves also change, and then finally, after 100 time steps, they look like this. So as we can see here, the mean of the green curve, which is action 3, is close to 0.65, and which is the true mean, which we decided earlier. So the bandit figured out over time what are the true means is. It's still a little bit uncertain about these actions. So if we run the bandit for more time steps, we can see these curves shrinking even more. But at least now we can do some statistical analysis on top of these distributions, and we can confidently say that arm 3 or the layout 3 is the best one, and we should use that. So I have another graph here where we are not exploring, we are performing greedily. So what I mean by that is, the bandit interacts with the environment, and the first couple of interactions gave a reward of 1 for the arm 2. So if the bandit acts greedily, if it does not explore, bandit will think that arm 2 is the best, and it will keep on executing arm 2. No wonder that the final distribution it learned for arm 2, it's correct, like the mean lies close to 0.5, but this is suboptimal, like the bandit has converged to a suboptimal solution. It does not know anything about arm 3. So this is the problem with the greedy approach, and that's why exploration helps. And this clearly highlights the importance of exploration in a case of partial feedback situation where, we have to discover which action is best by executing it. Okay, so finally, let's look at the performance plots. So I told you that bandits try to minimize cumulative regret. So I have cumulative regret on the y-axis. X-axis is just time steps. And then we are looking at the regret of three different ways. The red one is the Thompson sampling one, which I just showed. It's the best one. Green is greedy. This is almost linear because it has converged to a suboptimal solution. And then we have A/B testing here. The blue curve is for A/B testing. For A/B testing, in this case, what we did was we just ran a period of uniform exploration for 100 steps. What that means is we just allocated 33% of the traffic to all the 3 layouts. After collecting 100 data points, we decided that, hey, layout 3 looks like the best. Let's just always show layout 3 to the users. So this is how the curve for A/B test looks like. Now here, 100 is actually a bad assumption. It will be way worse in practice if we do some statistical analysis to be sure that actually layout 3 is the best one. But you get an idea that A/B testing, the percentage of traffic that goes to different layouts is fixed over the course of experiment. But for Thompson sampling, we are constantly adjusting it so that we direct more traffic to layout 3, which is the best one. So this is why bandits are really good if you want to do A/B testing. Okay, so that was all about simple bandits or multi-armed bandits where there was no context involved. So what does context mean? So context is just any other auxiliary information that we can exploit to make more informed decisions or better decisions. So contextual bandits is just an extension of multi-armed bandits to take context into account. And this context can be of 2 types. So now I want you to think from the perspective of a movie recommender system. Let's say we want to build a movie recommender. So what all features we can have? So we'll have user features. We might have features for different movies or different items that we want to recommend. So we are categorizing those 2 types of features here. So shared context, in this case, in the context of a movie recommender system, becomes the user features because these features are shared across all the different items or the arms whenever the bandit wants to make a decision. Action-specific features are the movie features. So each action can be specified with the feature vector. This feature vector can capture things like what genre of the movie is, what's the cast, who's the director, and so on. Okay, so under the hood, what's happening now? We still learn a queue function, which is the queue value or the mean reward for every action. But the difference, sorry. Yeah. Yes, yes. No, so shared feature is the feature that is shared across all the actions. So the genres that you're talking about, they will be common to all the items, but they will be different. So item 1 might be an action movie, so the feature will be different. Item 2 might be, an animation movie, the feature 2. Yes, exactly, yeah. And in this case, the user features will be same across all the AMPs, yeah. Okay, so under the hood, what's happening here? We are still learning a queue value. The only difference is that the queue value is now dependent on the context and not just the action itself. So estimating this queue value becomes a little trickier. We can no longer just maintain the mean of rewards that we have seen so far because we have a context vector there. So what we can do is we can learn a queue model using online linear regression. So this is a very simple model. So phi of S and A are the context vectors that I just talked about. And then theta is the weight vector that we want to learn for this linear regressor. It's not necessary to use a linear regressor. We can use more complex functions like decision trees, neural networks, and whatnot. But the problem here is that bandits, if they learn in an online fashion, then it's the best because they want to minimize the costs. So they want to update their weights as soon as possible. With decision trees and neural networks, online learning is not possible. So online learning means that we can change the weights by just using one sample of the data. Neural networks, as you know, they usually operate on mini batches. They require a large amount of data to learn a decent model. Decision trees, you have to always retrain the decision trees from scratch on all of the data, even if you have one new data point. So that's the problem. Other problems are related to exploration strategies. The exploration strategies that I talked about, UCB and Thompson sampling, they are based on uncertainty estimates around the weights or whatever the model is trying to estimate. With neural networks and decision trees, that gets even harder. So this is a very active research area. People are still working on how they can use neural networks with bandits with exploration strategies. But for the sake of simplicity, in this talk, we just focus on online linear regression. So coming to exploration strategies, which operate on top of the Q model, epsilon greedy still remains the same. There is no change. UCB and Thompson sampling evolved to Lin UCB and Lin Thompson sampling. And if you recall, earlier we were maintaining uncertainty estimates around the Q values. Now what we do is we maintain the uncertainty estimates around the theta. That's the weight vector of the linear regressor that we are learning. So graphically it looks like this. Let's say that our feature space is just two-dimensional. We have this theta here. What we do is we maintain a confidence ellipsoid across this, around this theta. And as we learn over time, this confidence ellipsoid will shrink. And we hope that this will get closer to the true theta star that we are trying to learn. How do we explore? We somehow, using math, take these uncertainty estimates in theta, and we then translate them to the uncertainty estimates in Q value. That's easily possible with linear regression. We get a very good closed form solution. And again, just to reiterate, this type of analysis gets way harder with decision trees and neural networks. Okay. So another extension to contextual bandits. So in practice, again, it doesn't make a lot of sense if we just recommend the top one item. We have to recommend a list of items. So how do we make the bandit do it? A very simple extension that I have here is, you just score all the items that you have and pick the items with the top case scores. Okay, so that's how you do the inference, you make the predictions. But then how do you learn? You are no longer recommending just one item. You are recommending a sequence of items, which we call slate in this case. So generating reward can get a bit tricky here. We don't know how the user will look at this list. User, in the worst case, might skip all of these items, go to the bottom of the page, and do random things. But for the sake of simulation and just to get some decent idea of how the algorithms perform, we have to assume some user model. So what we do is we assume a cascading click model here. Now this model is very simple. It just tries to simulate user behavior. We assume that the user is scanning this list of items from left to right. If the user is interested in an item, user will click on that item. We give a reward of 0 to the items before the item that the user clicked on, assuming that user saw these items but didn't like them. And we don't generate any feedback for the items after the clicked item because, again, we assume that user did not look at the items after that. So that's the cascading click model. And then what we do is we take these 3 rewards, we feed it back to the bandit, and then bandit can learn on these 3 experiences. It ignores the fourth one. Yeah. Okay. So now we'll see how contextual bandits perform on a recommender system, on a movie recommender system. We train a movie recommender system on the MovieLens 100K dataset. So Bharat is going to explain that how we do it. But before we get into that, let's see how these bandits perform compared to the traditional matrix factorization approaches. So again, I have cumulative regret on the y-axis, x-axis is time. The orange curve is the worst one because the cumulative regret is the highest. It's a random algorithm. It just recommends random movies. The second one is neural matrix factorization. So it performs matrix factorization, which is it basically learns latent user and item features through SGD. It's a neural network-based model. And as we know, neural network cannot learn online. So what we have to do is we have to train this model on historic data again and again as we collect more data. And we cannot update it with every interaction because that will be too expensive. So we choose to update the model after every 50 interactions. Then we have Lin UCB and Lin TS, which are the contextual bandit algorithms I just explained. They make use of movie features like genres and everything. They almost perform the same. And the best one here is collaborative bandits. So I haven't talked about collaborative bandits, But just to give you a high-level idea of what they are doing is, they are an implementation of online matrix factorization. They're also learning user and item latent features over time. But what they have inbuilt is exploration. So they maintain some uncertainty estimates around these latent features, and they explore in a way similar to Lin UCB. So that's the thing. Just to conclude, there are two reasons, primarily two reasons why bandits perform better than neural matrix factorization. First is online learning. We are capturing user feedback as quickly as possible. If the user does not like a movie, we just quickly train our model, and we update the parameters so that the next time we make a recommendation, we include user preferences, user feedback into account. And the second reason why bandit algorithms perform better is exploration. So if we have a lot of, again, new users, new items coming in. So in this simulation, we are simulating the perfect cold start situation. We start from 0, where we have 0 data, and then we learn over time. So as we can see, like, bandits are performing the best. Okay, so that's mostly about it. Now Bharat will explain how we can train a movie recommender using SageMaker RL. Thank you.
So I'm going to explain how we can use contextual bandits in SageMaker with an example taken from MovieLens dataset. So let me give you an overview of how this online recommender system is going to work first. We have a bandit model that's going to give us the recommended movies. We feed the user features, such as the metadata from age or gender, and latent features which we can compute from past interactions. And we can take the item catalog, shortlist it as needed per business reasons, and then feed that candidate list as well as the features that they may have. So in case of movies, it could be genres or director name and so on. And then the bandit agent takes these as inputs and generates the set of movies that this particular user might like. Then the user clicks on one or two of these items, and we log both the implicit feedback, which is through clicks or view time, or explicit ratings that the user might assign to these items. And then based on that, we compute the reward and retrain the bandit. And this loop continues until the bandit improves over time. So we are going to create a simulator to capture how the user behaves given different recommendations. And this simulation is going to capture all the inputs and outputs to that bandit agent. So it picks the users and the candidate items. How do we compute the rewards? How do these different features get generated, and so on? And the rewards are then fed to the agent and to allow it to learn across time. So I'll explain how we construct the simulator for the MovieLens dataset. So in the MovieLens dataset, we have interaction data, where we have a user rating a particular movie. So the dataset looks like a series of users and the corresponding movie and what rating they give. Now, from this, we pick a user randomly one at a time for each interaction, and we generate a candidate list of movies that this user may like. And how we get the candidates is like take the data set and see all the movies that the user has rated, and then use that as the candidate list for this set of the candidates that the bandit agent will look at. And the reason we look at this different set of movies that the user has rated, because we know the ground truth. We can take the rating and say, hey, if the user gave a rating of 5, with probability 1, the user will click it. If they only gave a rating of 3, we reduce the probability to 0.6. And that's how we compute reward. But in the computation of the reward, we also take into consideration the user choice model. In this case, we use the cascade click model that Saurabh explained. One thing to note is that because the candidates' movies are based on how many movies the user rated, the candidate list is different for every user. So it's dynamically changing for each time the bandit is interacting with the client. So you have this client that captures all of this and interacts with the SageMaker bandit agent. The client sends the user features, the candidate movies, and the movie features. The bandit agent responds with the movies that this user might like, and the client then sends back the rewards. So let's see how SageMaker can use this simulator to learn a bandit agent. So we have two different modes of training this bandit agent in SageMaker. One is what we call as experiment workflow. where it's meant for data scientists who want to understand how the algorithms are working, identify what are best hyperparameters for this algorithm, what features work best for their data set. So the interface is a SageMaker notebook, from which we can launch a training job. A training job spins up a new machine and launches a Docker container within which all the training happens. Inside the Docker, we instantiate our simulator and the agent, and they start interacting to collect an interaction data set consisting of state, action, and rewards. So state with user features and item features, action being the recommended movies, and the rewards that were gotten based on the computer choice model and the ratings that were provided. And then we use that data to update the agent, and then the updated agent is then used to collect more interaction data, and this loop continues until the model is fully trained and the rewards saturate. We save all of the data to S3 for visualization, replication, and diagnosing what might have gone right and wrong. While this is the experimentation workflow, we also have a deployment workflow where we want to scale out and implement this in production. And this will handle things like low latency, high throughput, and scale the infrastructure needs as needed, taking a lot of the workload out of the developers. So let's say we have some historical data. We can do what we refer to as warm start and initiate a model based on the data that you've already collected. This model we then evaluate using offline model evaluation algorithms. And this gives us an idea before we deploy it to production how good the model learned is and whether you really want to deploy it or not. Once we are satisfied, we deploy it to a SageMaker endpoint, which hosts the model and allows us to ping the model to get the movie predictions we want. If we have no historical data, then we can start with some model that you already have, or we start from scratch and the model is going to start with some random recommendations. The client application now interacts with the hosting endpoint. It provides the state, the user features, and item features. And the bandit now provides the recommended action and also the event ID. So the event ID is the unique ID that we are going to use to track every interaction, create our data set for further updating and training of the models. The hosting endpoint automatically logs all of the requests and the resulting predictions to S3 using Kinesis Firehose. And the client application is also expected to provide the corresponding event ID and the rewards that you got actually from your system. These rewards can be different metrics that you care about, such as click-through rate or the revenue that you received. Then we process the data that was logged from the hosting endpoint, as well as the client application using Athena, and then create the data format that is required to retrain the model. Now we have a new model that we train using SageMaker training, and then we use offline model evaluation to see if this new model is actually better than the model that was existing before. And this loop continues on, and the model slowly improves over time, and so, it gives us better recommendations. We have demo notebooks that show how both this experimental workflow and deployment workflow works, and both of them use contextual bandit algorithms that Saurabh just explained. So with that, I'm going to switch to reinforcement learning, where there is a number of different features that are supported in SageMaker and how that is, you can use it for different applications. Reinforcement learning is like a superset of bandits, where it is, instead of optimizing for a single action, it's optimizing for a sequence of action that will result in maximizing the total rewards that you got over those set of actions. There are a number of different applications that reinforcement learning enables. We classify them broadly into simulation-driven and data-driven. Simulation-driven applications include games and robotics and industrial control. And here, we create a simulator that captures what will be actually happening in the real world. The challenge with these applications is that you want to create a simulator that is as realistic as possible so that the model that you learn in simulation can be deployed to the real world. And then we have data-driven applications. Contextual bandit algorithms that we presented were an instance of these set of applications. And other applications include supply chain, resource allocation in computing, again, recommendation systems where it takes sequence into account, and so on. So this slide provides an overview of what we have in SageMaker RL. All of the RL algorithms are building on success of the deep learning frameworks. So everything is built on top of frameworks such as MXNet and TensorFlow and PyTorch. We support two state-of-the-art RL libraries called Coach and RLlib, and they implement the latest and the greatest of the algorithms that are coming up in the literature. All of these algorithms are exposed through a common interface called OpenAI Gym, so that you can plug in whatever the particular problem you have that conforms to this interface, and all these algorithms can be used against that. We provide a lot of different simulation environments, some of which are by AWS itself, such as RoboMaker for robotics, Sumerian for virtual environments. We support open source environments like Energy Plus, which is used to simulate air conditioning systems. And for robotics, we have RoboSchool and PyBullet. And then there are commercial simulators such as MATLAB. This hierarchy allows us to support a variety of different domains and the corresponding problems in them. Let me give you a brief idea of the different kinds of ways we can train a reinforcement learning agent. I'm not going to dive too much into the algorithms themselves, but instead trying to capture what kind of different simulators you might have and different kinds of live environments where you might do data-driven reinforcement learning. So in this case, this simulation environment and RL agent packaged into a single Docker container. And the training happens within that container, and the interaction data is collected and used to update the agent. And this cycle, just like the bandits, is used to train the RL agent. Then we save the trained model, and we can deploy it to a hosting endpoint or take the model and deploy it to a device, such as in robotics. We have provided a number of different examples that use this. For example, we have a financial portfolio management that takes existing data set and creates an OpenAI Gym simulator. And then we train the RL agent to make decisions on how much stock should you be buying or selling based on what has happened historically. We also have an HVAC energy optimization example, which uses this Energy Plus simulator, which is a state-of-the-art simulator provided by US Department of Energy. It may not be always possible for us to package our simulator in a Docker container and then use that in a compact way. So SageMaker 1 provides another way of doing RL training where your simulation is considered remote, and you can have any kind of simulator that is just simply interacting with the SageMaker during training. So in this case, we have Deep Racer as an example, which is a 118 scale car that teaches you concepts about reinforcement learning and machine learning and how you can use that to autonomously navigate a track. So here, the simulation is done in a different service, RoboMaker, and a copy of the agent is provided to RoboMaker, and the simulation also happens inside RoboMaker. RoboMaker collects the interaction data and stores it in a database. And from that database, SageMaker ingests that data and updates the agent. The agent then stores these models on S3, and RoboMaker periodically downloads the data from there, and this loop is what allows us to train the agent. We can periodically save the agent to S3, and the saved models can be deployed to the robotics car like Deep Racer. One thing to note is that we can do distributed training. As reinforcement learning solves more and more complex problems, the bottleneck comes with how fast we can collect this interaction data. So for both the architectures that I explained here, we can parallelize the simulations such that we collect interaction data much faster, and that allows us to train the models in a very timely manner. Here is an example of how Deep Racer is training across 4 different tracks with 4 different lighting conditions that allows the resulting model to be more robust, and as well as train the model more quickly. And finally, we have an architecture where the reinforcement learning agent is training against a live environment. This is the same architecture that the contextual bandit algorithms use to interact with the client application. So the model is deployed on SageMaker hosting endpoint, and the client application interaction is collecting the data in a database or S3, and SageMaker is again ingesting that data to update the agent and so on. We have provided a number of different examples which are open source on GitHub that covers domains across autonomous robots, HVAC energy optimization, neural network compression, resource allocation, and also includes the bandit examples that we covered earlier. This includes use of multiple deep learning frameworks, different algorithms, multiple RL libraries, just to provide a variety of different use cases that might be fitting to your particular problem. I'll leave you with a brief overview of how DeepRacer works with this video. With that, thank you so much.